Let's now talk about the independent samples test. So in a one sample test, we compare the test value or hypothesized mean to our sample statistic, sample mean, right? In independent samples test, we will compare two groups' means. So group 1 mean to the group 2 mean. That's it. That's the only difference. And the z-value calculation is going to be a little different because it will be mean 1 minus mean 2 divided by a standard deviation that is found by taking into account the dispersion of the two different sample distributions that we have, which is equal to this formula right here, standard deviation of group 1 divided by the number of sample size, total number of samples that we have in group 1, added to the standard deviation of group 2 divided by the sample size of group 2. You add these together and then take the square root of this number and you get a standardized standard deviation of the two groups, which is called the standard error of the differences between two means. So it's denoted as follows. It's Sx bar 1 minus X bar 2, and it's the standard error of the difference between the two means. This is difference between the two means, and S stands for standard error. So let's now go ahead and do the example. A researcher proposes that if a product package is red, attitudes towards the product will be different than they are with the current blue package. Hence, he decides to conduct a test across two groups. He packages some products with his proposed red dominant packaging and some with the current blue packaging. He surveys 164 people about the red package and calculates that people respond on average 4.5 on an interval scale of 1 to 5 about how much they like the product, with a standard deviation of 0.5. He surveys another 164 people about the blue package and calculates that people respond with an average of 4 on an interval scale of 1 to 5 about how much they like the product, with a standard deviation of 0.4. So if he has these results, is the red package indeed more effective? Let's go ahead and calculate. So we are now using the z-score approach, the critical score approach, the critical value approach, and we will actually no longer do the p-value approach or the confidence interval approach for the independent samples, t-tests, or z-tests, but know that they exist for independent samples too. They are the same logic. And also, if you have sample sizes less than 30 for independent samples tests, you use the t-test. And if you have sample sizes larger than 30, you use the z-test. So similar ideas to the one sample test. And I'm glad I have slides, because before anything, with this research question in mind, let's write our null and our alternative hypotheses. Our null hypothesis is that the group 1 is going to equal to the group 2 mean, because that's the status quo, right? There's no difference between my two groups. Treatment was not different than control. And then my alternative is that they are indeed different. what I want as the researcher. So now let's go ahead and calculate the observed z-score. Z is equal to mean of group 1 minus mean of group 2 divided by the standard error of the differences between the two groups. And that is equal to the first group's mean is 4.5, right? So X bar first group is 4.5. The researcher said the standard deviation is equal to 0.5. The researcher said, he said the number of people in group 1 is also equal to 164. X bar 2, the second 164 people, he asked about the blue package, said that on average they are 4.0, and then their S was 0.4, and the N for the second group is also 164, right? So let's just plug these in. First group's average mean 4.5, second group's mean is 4.0. These are the means for two groups. Now let's calculate the standard error for the differences between the groups. It's going to be like as follows. S1, 0.5 divided by 164 plus S2, standard deviation for the second group, 0.4 divided by 164. Squared. You square the standard deviations for the two groups as well. So 0.5 squared divided by 164, 0.4 squared, 164. Later we'll take the square root to just basically account for the squaring of the two standard deviations. Basically, you take the variance of group 1, variance of group 2, right? Because standard deviation for any sample squared is equal to the variance. So then we go ahead and calculate this. So 4.5 minus 4.0 is 0.5. And then this beast over here calculates to be square root 0.0025. You take that square root and that equals to 0.05. That equals 10. So our observed z-test value is equal to 10. And our z-critical is 1.96 plus minus 1.96, right? So our z observed is larger than our z-critical because 10 is greater than 1.96. Therefore, we reject the null. What does this mean? This means that the means for the two groups are statistically significantly different than each other. And you can infer that the two populations for the people who looked at red packages and blue packages are indeed different. And people indeed react statistically significantly differently to red packages than they do to blue packages. Consumers truly evaluate the red package different than they evaluate the blue package. And, I mean, you only can infer about the difference between the two means because we're doing a two-tailed test. But looking at the means, just comparing the two means, I can also... the two means that are statistically significantly different according to our independent samples test, I can say that x1 is equal to 4.5 and x2 bar is equal to 4.0. I can say that group 1 evaluates packaging higher then 4, then group 2. And group 1 was looking at red packages, so red is evaluated higher, statistically significantly higher than blue. So non-directional two-tailed tests, what we were doing for the one sample and independent samples tests that we were conducting here, our hypotheses can actually, so our hypotheses, when we were doing the two examples, were non-directional. So we were doing two-tailed tests, meaning we said mu1 is going to be equal to mu2, or mu1 is going to be not equal to mu2. This was null, and then this was the alternative. Similarly, for the one sample, we said that mu is equal to the value, hypothesized value, and mu is not equal to the mu hypothesized. These hypotheses do not include a direction. Let me tell you what I would mean by direction. I did not say that mu1 was going to be larger than or equal to mu1, and then, mu2, and then mu2, it was going to be smaller than. So this would be my null. Like, I did not suggest any direction in terms of which mean can be higher, or in other words, I did not suggest directionality for my means. If I do, then my critical z's change because how I distribute the probability across the curves change a little bit. So I either look at the probability at the two ends or the probability at one end only. But this is not going to come up in the exam. I just want you guys to know that we are going to only do non-directional tests in this class. We're not going to do directional tests at all. But your z-criticals, when you were doing the tests, would change if we were doing directional tests, one-tailed tests, where our hypotheses would suggest directionality. I just want you guys to know this. So for your information, there is this concept of suggesting a direction or not for your hypotheses in statistics. Honestly, not very much used in research either. So know that, you know, your z-critical scores could change in terms of suggested directionality if directionality is suggested in your research questions. Lastly, I'm going to talk about something that you guys all covered in statistics classes, where if your null is true, and you fail to reject your null, then you come to the right, the world of no error, world of correctness. Similarly, if your null is false and if you reject your null, these two green boxes is where we want to be as researchers. And sometimes we make mistakes because statistics is purely reliant on probability, right? Sometimes just by probability, we're going to be wrong. And in those cases, we're going to be conducting some errors. So if your null is equal to, if your null is true in the world like this is known kind of a thing. If your null is true, but you still reject your null, saying, oh, my two group means are different from each other, while they are actually not in the true world, like known world, then you would commit a type 1 error. So basically, you got maybe like 4.4 in terms of evaluations from group 1, and then 4.3 from the other group, but somehow statistically you ended up saying these two are different because your z-score was high enough. You would be conducting a type 1 error. And if your null is false, so actually this is true, so your null is false, but you failed to reject the null and you said my mu1 is equal to my mu2, but this is not correct, then you would conduct a type 2 error. For exam purposes, if you know this chart, that's good enough. You don't have to explain type 1 or type 2 errors for me. But the logic that you need to know behind type 1 and type 2 error is that we rely on probability in statistics, and sometimes we are wrong just by the nature of doing things, and our point of view at looking at the world is a little bit odd. We think of like null and not null, and z-score is like furthest enough from 0 so we can reject the null kind of ideas when we are talking about our statistical results, which is not really very straightforward because we don't use this a lot in the real normal world. So that's all I want to say. I am going to talk about SPSS next. SPSS, running the one sample and independent sample tests on SPSS.